can blink, but not move. Not chew, swallow, breathe. Not talk, communicate. Locked in your own body while being fully aware. Of all the inabilities, a lack of communication may place a tremendous burden on the mental well-being of those suffering from locked-in syndrome. Social media is by no means a replacement for social interaction, but it is an addition that allows us to meet new people and check up on our loved ones, wherever they are and wherever you are. At BrainBrowsR, we want to unlock social media for people with extreme paralysis, ALS, or locked-in syndrome. To do so, BrainBrowsR uses a browser extension, Xtension, to transform web elements into flickering boxes. Looking at these flickering boxes generates a specific electrical signal in the brain, which we measure using commercially available neurotechnology. The brain data is sent to the computer, which analyzes what the user looks at, using our analyzer software. This process flow allows users to interact with the web only by using their eyes. Of course, there's much more to this technology than meets the eye, so let's go take a closer look.
At the core of BrainBrowsR is Xtension, a browser extension that inserts periodically flickering stimuli into the web page using JavaScript. Because we use HTML elements and stimuli, they can be easily animated via CSS, which gives developers a lot of opportunities for web-based brain-computer interactions. Each frequency of a stimulus corresponds to an action on the web page, for example liking a post or scrolling to the next one. These frequencies are attributes of a CSS animation that changes the element's opacity according to a sine wave. When the user focuses on a specific interactive element, flickering at a certain frequency, the brain reacts accordingly.
While all stimuli on the screen are in the user's field of view, the occipital lobe of the brain reacts strongest to the stimulus that the person is focusing on. Because of the repeated sensory overload of the eyes, the brain generates an electrical potential called a steady-state visually evoked potential. In order to measure this potential, we need specialized hardware, an electroencephalogram headset. We tested out various headsets, but were astonished by how well the Mentalab Explore worked with dry electrodes. While being the largest cost of BrainBrowsR, it is relatively cheap and commercially available. It does not require gel, it is easy and quick to put on, and the electrodes have a small height, which makes lying down on a cushion comfortable. The electrodes measure the electric potential of the brain at the occipital lobe. A device amplifies this signal and is sent via Bluetooth to the computer, where it is processed by analyzer.
The signals obtained from the EEG headset are famously noisy due to power line noise, electrode noise, movement artifacts, and other brain activity. In the frequency domain, we start by applying a notch filter. That will filter out the 50 Hz signal. Afterwards, a Butterworth bandpass filter is applied, which has a flat passband characteristic, leaving us with a frequency spectrum of interest that contains the stimulation frequency and their harmonics. Depending on the number of harmonics we will consider in our classification algorithms, the frequency band can be extended. After the data is processed, analyzer starts by analyzing which stimulus the user is focusing on, a process we call classification.
Classification is a process of a computer recognizing and classifying objects within a dataset. In our case, these objects are frequencies corresponding to the different stimuli, and our dataset are the brainwaves. We use three paradigms: canonical correlation analysis, extended CCA, and Riemannian geometry. In CCA, for each of the possible frequencies, we calculate the correlations between a sine and cosine of the frequencies, their harmonics, and the brainwaves. The highest correlation will be the most likely frequency and subsequent target on which the user is focusing. The advantage of CCA is that there is no training required before each session, but it is less accurate than extended CCI or Riemannian geometry. Which paradigm is used depends on the user-specific sensitivity to SSVEP signals.
Once a dominant frequency has been recognized, we have to check that the user is in fact focusing on the corresponding stimulus. This is done by storing 3 samples of EEG data and taking the difference between the 2 best predictions, resulting in a measure of certainty for the predicted outcome. We then attribute more certainty to frequencies that are consecutively predicted and average each over time. A threshold is established by a single calibration session. If the certainty is higher than this threshold, the index of this frequency is sent to extension via WebSockets. WebSockets are used to communicate between the data processing code written in Python and the browser extension written in JavaScript. First, a connection is established between the browser and the Python server through the internet. This connection can be used to send messages. A listener is waiting on data processing for a message. On receiving this message, the extension can take an appropriate action. The nice thing about WebSockets is that they can be used to send messages in both directions, like for example, alerting the Python server that something has gone wrong in the extension. If everything went well, the extension is now able to perform a web interaction.
To have the extension perform an action, we need a parser and a processing function. The parser finds specific elements in the HTML code using CSS classes and HTML tags. HTML elements that have the same class can be differentiated between using their parent containers. Once the elements of interest have been found, a processing function executes an action. Some of these actions are broadly used, such as going from a previous or going to the next section. Other actions are web page specifics, such as liking a post. In any case, it's very simple to add new interactive elements within our codes. This makes BrainBrowsR extremely adaptable. That was the technology behind BrainBrowsR, but what would be the impact of people using it?
Another important aspect that needs some consideration are the patients themselves. We contacted several health institutions and patient organizations in order to gather information that can be used in the design of our application. An interview was conducted with Professor Steven Laurijs.
Quality of life correlated with the capacity to connect to others. And so I think that study tells us what you do is important, and we need those technologies to, first of all, give them a voice, give them the capacity to express their own thoughts and wishes to the ones around them, but then of course also with the internet.
Yeah, so yeah, you mentioned already some benefits if you can get them access to social media, like for social interactions, etc. But do you also think there can be some negatives to giving them access to social media, because everybody is living, like, how do you say it, their best life in social media? Can it be confronting for locked-in patients, or?
Well, there's many challenges, but if you ask patients, I think they would be terribly happy, and these are really minor problems as compared to what they're going through.
We also asked Ujjwal Shutari, postdoctoral researcher in Tübingen and founder of ALS Voice, what the outcome could be of giving ALS patients the opportunity to access social media. This painting you see was made by an ALS patient. She enjoys receiving pictures from Dr. Ujjwal, who visit different places, like we see on Instagram, in order to make a painting out of it. After knowing the needs of patients and being motivated for its potential impact, we wonder how to continue with such a project.
Many NeuroTechX student teams, present and future, might ask that question. A team of 15 creative and well-educated students is only able to do so much. To gain more information on how companies start in the field of neurotechnology, we went to Metronic, the largest medical technology company in the world. Among numerous helpful advice and interesting questions being asked by Metronic's experts, we learned that companies such as Metronic take initiatives such as the Eureka program. Through it, anyone can propose new, innovative ideas that could grow into beneficial medical technology companies. One day, BrainBrowsR may be one of those companies, but first, improvements have to be made.
Indeed, during the project we have faced many challenges, of which some have been solved and some unsolved. Firstly, the stimuli had to be consistent, and doing this in a browser is difficult. We experimented with many parameters such as color, size, distance, and shape to get the best results, along with adjusting built-in browser parameters. But there is room for improvement. Secondly, we had created code that is able to transform any existing HTML element into stimuli. However, the results weren't nearly as good as with the GUI stimuli. A next step would be to combine this with eye tracking to increase its effectiveness. Lastly, obtaining a stable connection between the headset and the web page is difficult. We have optimized our coding as much as possible in this regard, but other methods have to be tested that allows a larger variety of headsets to use BrainBrowsR. We have worked hard to solve as many challenges as possible. As a team which will now show you BrainBrowsR.